NN based backstepping control. This will be the topic that we will be discussing. This is the topic under our module 3 neural control. This is the lecture 10, NN based backstepping control. In the last class we learned a very preliminary idea about neural network based control. Now we will introduce a new concept called backstepping control using neural network. We will be covering following topics: NN based neural network based adaptive control, that Lyapunov based controller design, backstepping method, backstepping control design using neural network. We will apply this method to a rigid link electrically driven manipulator through simulation, and finally conclusion. So, this topic we already discussed in the last class, NN based adaptive controller, neural network based adaptive controller. I will just give you a little hint. So, for this, if I select tau equal to f plus VMR plus KR, the closed loop error dynamics is MR dot is plus KR equal to 0, which is actually stable dynamics, because M is always a positive definite matrix. And so, this is a stable dynamics provided K is properly selected. You can easily see that this is actually the computed torque control. In principle, this is actually computed torque control, but to implement this controller, f must be known. F means this quantity must be known, but unfortunately we do not have many parameters with us to compute this exactly, and hence we estimate f by f hat x, and we approximate this as a radial basis function as a kernel in which w is the weight vector and phi x is the basis function, and this phi x is function of these quantities qd double dot, qd dot, e dot, e dot and q. And you can easily see also this quantity is a function of qd double dot, e dot, qd dot, e and q, and that is exactly is here qd double dot, qd dot, e dot, e dot, e and q. So, the and phi x are the basis functions. So, this can be represented in terms of a radial basis function network, which we have already discussed in neural network model. So, f x, so W is the weight matrix for the neural network, and W transpose is the optimal weight matrix. So, that nonlinear function f x, this f x, this f x can be expressed as W transpose phi x. So, now the objective is that we do not know, we know what is phi x basis functions, because we know the input, but we do not know what is W transpose. So, we have to update the weights in such a way. So, we have to find out what is this W hat dot, such that we can again establish the system is stable. So, that we always do using a Lyapunov function method. So, what you do now, instead of tau equal to f plus kr, we write tau equal to f hat plus kr. You see that tau is f bmr is missing here, Okay. We also assume Vm also is unknown, in that case tau is f hat plus kr. The closed loop aerodynamics is mr dot is f minus f hat minus kr minus Vmr. So, which is this quantity f hat minus kr minus Vmr. So, this quantity see usually earlier we used to have tau is f hat kr plus Vmr. In that case this Vmr used to cancel out, and f and f hat, if they are exact, then simply mr dot is minus kr, but now we have extra term here, this term and this term, and we have to find out what is w hat dot such that the closed loop aerodynamics is stable. So, the closed loop aerodynamics stable is w hat tilde transpose phi is bounded. For this we consider a Lyapunov function, which is L is half r transpose m r half trace w tilde transpose gamma inverse, gamma is a positive definite matrix, w tilde. So, its time derivative of this Lyapunov function is half r transpose m dot r plus r transpose m r dot plus trace w tilde gamma inverse w tilde dot, and you know that w tilde dot is simply w hat dot, because if you look at here w tilde, which is here f minus f hat. So, w tilde is w tilde is w minus w hat. So, w tilde dot is minus w hat dot. So, this so going back here, you can easily see that we can r dot, if you replace r dot which is m inverse this quantities. So, this quantity is this quantity r transpose m r dot. If I replace r dot from here, I finally get minus r transpose Vmr minus r transpose kr minus r transpose w tilde transpose phi. But you see that because of skew symmetricity, this quantity is 0. This two quantity is 0 skew symmetric property, and so finally L dot is minus r transpose kr and these two terms. So, if I take w hat dot is gamma phi r transpose, then L dot is, as I said, this is 0 because of skew symmetric, and if I select this, then this quantity is same as this quantity. Okay. So, they cancels out, this quantity is same as this quantity. So, your rate derivative of Lyapunov function is minus r transpose kr. Okay. So, this ensures the boundedness of approximation error w tilde transpose phi. It can also be shown that V double dot is bounded, and by Berbol's lemma r tends to 0 as t tends to infinity. So, it is not simply stable, it also says that the tracking error will converge to 0. So, this particular what we showed that this is a neural network based direct adaptive control, where my control law is given by this particular thing and my weight update law is given by so weight update law is given by this particular expression w hat dot is gamma phi r transpose. Now, we will go to the backstepping concept, how we can also utilize backstepping concept to design neural network based adaptive control, direct adaptive control for very complex systems. I will just introduce a little concept of Lyapunov based control and backstepping control. You see that this is our simple scalar differential equation. X dot is a cos x minus x cube plus u. U is the control action and x is the state of the system. So, the objective is that the task is to design a feedback control law which globally stabilizes the equilibrium at x equal to 0. Now, consider a Lyapunov function candidate V x, which is half x square because x is the only state. So, you can easily write down this. So, its rate derivative, the rate derivative or time derivative V dot is x x dot, which is x, and x dot is cos x minus x cube plus u. So, if I select u to be minus cos x minus x, so you get V dot is minus x to the power 4 plus x square. You can easily see if I replace one here, this term cancels out, okay, and inside minus x cube minus x and outside x, if you multiply, you get minus outside x 4 plus x square. So, this is always 0, so the system is globally stable. So, this is my control law. So, this is my control law, u equal to minus cos x minus x. This I am finding out simply applying the Lyapunov function. Now, in a Lyapunov based design, if I am given a nonlinear system, a vector equation, x dot is f x u, x is a vector, f is a vector, u is also another vector. The task is to design a feedback control law u equal to alpha x such that the equilibrium point x equal to 0 is globally asymptotically stable. The design step is always, so you find out what is a V x as a Lyapunov candidate, then you find out what is V dot x, the rate derivative which you can write as del V, dou V upon dou x into f x u, because V dot is this quantity is dou V by dou x dx by dt. So, this quantity is dou V by dou x x dot. So, this x dot is f x u if I put, and if this is always less than some positive definite function w x, then this is Lyapunov stable. But what is the problem? Problem is, for a higher dimensional system, it is usually difficult to find a suitable Lyapunov function V x and w x, even though the system is stabilizable. For a scalar system, control design is simpler. So, motivation now for a backstepping control. Is it possible to divide a higher order system into a number of scalar systems and design control for each one of them, and then finally integrate all these individual control actions to find the actual control for the plant? Now, the example. So, what I am trying to say here is that because we saw that for a simple system like a scalar differential equation, which was earlier given here, there is a scalar differential equation. For this, the control action, designing a control action was very simple. But if complex systems, a vector differential equation is there, so can I divide this vector differential equation to simple subsystems, and such that each subsystem, for each subsystem I can design a control action using Lyapunov function. Is it possible? So, now we will see that how we can do that. Now, you see that here it is a vector differential equation. We have two states, one is x, another is y. So, we have two states here, x, y. So, where the differential equation is x dot is cos x minus x cube plus y, and y dot is u. So, the task is to stabilize the system at equilibrium point. You can easily see that the equilibrium point here is 0 and minus 1. Okay. For the first subsystem, if xi were the control input, okay, this is the equilibrium point. Now we want to stabilize the system around this equilibrium point, and now we represent this is subsystem 1 and this one as 2. So, let us design a control action for this. Let us stabilize the first subsystem, assuming xi to be a control action, not as a state. Okay. If it is a state, then it is a double states are there, so it is difficult. So, it is better that I always assume that this to be. So, already we have solved this problem in the last example where xi was u. So, now instead of xi, I say this xi is simply a control action, virtual control action, let us imagine. So, so if I accept xi as a control input, then we have already shown in the last example V1 if half x square, then xi has to be minus x minus cos x, for which the system is stable, and we found out the rate derivative of this is minus x to the power 4 minus x square. So, now, but this xi is not a control action. I cannot give this xi from outside the system, this is inside. So, but xi is a state variable, not a control action. So, nevertheless, its desired value is known. So, what is meaning of that? If xi follows this trajectory, then this is stabilizable. So, desired xi d is minus x minus cos x. If xi d follows this trajectory minus x minus cos x, then the first subsystem is stable, that is very clear. So, what we do now, we introduce a new state variable instead of xi tilde, which is xi minus xi desired. Okay. So, what I do, I rewrite the first subsystem x dot as cos x minus x cube plus zeta. This was my original one. I add zeta d and subtract zeta d. So, by doing that, what I do, I write this equation cos x and this zeta d, you know that already I know this zeta d to be zeta d is minus x. Okay. Let me write here, we have already found out zeta d is minus x minus cos x. So, if I introduce this zeta d, so cos x goes out. So, what is left is minus x cube, and this particular term is xi tilde. So, xi tilde. So, x dot now in the new form is minus x cube minus x minus xi tilde, and xi tilde dot, okay, because xi tilde is a new state variables. So, I have to write down an expression for xi tilde dot, which is xi dot minus xi desired dot, which is xi dot we already know u from the previous expression, the original expression, and xi d dot, if I differentiate this, of course, this would become minus x dot minus cos x into x dot. So, if I write that, this will be 1 minus sin x into minus x cube minus x plus zeta xi tilde. So, you have now this 2, this is my subsystem 1 and this is my subsystem 2. Okay. We have to now show that whether this system is stable for, and what control action I should find out u, so that the overall system is stable. So, we first of all showed that x dot is stable provided this xi tilde is actually bounded, or it's 0, or xi is following xi d. So, now we have to find out the overall stability. So, to do that, we take the Lyapunov function, we augment the previous Lyapunov function v1 x, which is half x square and plus half xi tilde square. So, this is v1 x is half x square plus half xi tilde square can be written as xi plus x plus cos x whole square. Okay. And because xi d is minus x minus cos x, so xi minus xi d is xi plus x plus cos x. So, this is what is put it here, xi plus x plus cos x whole square. So, if I take the direct derivative of this Lyapunov function, I get x x dot. So, x dot is this quantity from here minus x cube minus x minus xi tilde and plus this one, if I differentiate this quantity xi tilde into xi tilde dot. So, xi tilde and xi tilde dot is this quantity. If I insert this quantity here, I get minus x square minus x 4 square. You see that minus x square minus x 4 square, and I can take xi tilde common here, put it x here, and this quantity all enters here. So, I can make this quantity vanish if I select u to be x minus 1 minus sin x into minus x cube plus xi tilde. Then v at 8 is minus x square minus x 4, that guarantees global stability. So, selecting u to be minus x minus xi tilde minus 1 minus sin x, this quantity, okay, we get, and replacing xi tilde is xi plus x plus cos x, we get v a dot is minus x square minus xi tilde square. So, this is if I take this quantity and put it there, I get v a dot is minus x square minus zeta tilde whole square, and this proves the equilibrium point is globally asymptotically stable, okay, because this is always negative definite. So, what we essentially did here in backstepping control, that first we simplified our first the stabilization problem by stabilizing the first subsystem, and then I augmented the Lyapunov function to define the global stability of the entire system. Now, instead of doing that, if I would have directly selected a Lyapunov function like this, and then I would have taken v derivative, Lyapunov derivative. So, this is what I am saying. Let us take the comparison. Let us try to solve the previous problem using direct Lyapunov method, where we consider following Lyapunov function candidate. So, you see that v dot becomes this quantity minus x 4 x cos x plus x xi plus xi plus 1 u. You can easily see that this, you can verify this to be the red derivative of v dot, because this is x x dot, and we know already x dot is x dot is cos x minus x u plus xi. So, x dot, so x x dot becomes this quantity minus x 4 minus x cos x and plus x zeta xi, this quantity, and this quantity is xi plus 1 into xi dot, and you know that xi dot is u. So, xi dot is u, and if I select u to be this quantity, then v dot is minus x 4 minus k xi plus 1 whole square, and this is less than 0 and the system becomes stable. But as xi tends to minus 1, because we are stabilizing around the equilibrium point 0 minus 1. So, when I xi goes to minus 1, so you can easily see u becomes infinite. So, the system is not stable. So, although it implies that here it is stable, but it is not so, hence the controller does not take the system to its equilibrium. So, this controller cannot be implemented. So, this is you see that by going directly if I assume a global Lyapunov function from the very beginning, designing controller is very difficult, whereas we had a very nice control law that guarantees stability here. So, now we will give the backstepping method generic. We took an example, last example was just we through an example we explained what is backstepping control. Okay. Now, we will give a general notion of backstepping. What is general notion of backstepping is that the system description must be in strict feedback form. What is the strict feedback form? The strict feedback form means x1 dot is f1 x1 plus g x1 x2. In the beginning, now you just assume this each element is simply a scalar, okay, scalar differential equation. Okay. So, x1 dot is f1 x1 plus g1 x1 x2. So, this is a scalar, this is a scalar, x2 is also a scalar. Similarly, x2 dot is f2 x1 x2, again a scalar function, g2 x1 x2 another scalar function into x3. Okay. They can be also vectors for the moment, you just try to understand they are simply individually each one is a scalar differential equation. And if I can represent any differential vector differential equation in terms of m scalar differential equation, then this is called strict feedback form. Fi and Gi, this is wrong. Simply this is, they are all scalars, I would say these are all scalars. At the moment I just assume they are to be scalar, okay, are nonlinear functions that contain both parametric and non-parametric uncertainties. So, this f1 and g1, f2 g2, f3 g3, fm gm, they are nonlinear functions that contain both parametric and non-parametric uncertainties, and these gi's are known and invertible. We assume that g1, g2, g3, gm, they are known and invertible. Note, backstepping can be applied if internal dynamics are stabilizable. That is, if each individual subsystems are stabilizable, then we can design a backstepping control for this particular form, which is called strict feedback form. Okay. So, you see that x1 dot is represented in terms of x2, x2 dot is represented x3, x3 dot is represented x4 until xm dot is represented in terms of external control action. So, the backstepping method was originally given by Kristic, Kanellakopoulos and Kokotovic in 1995. So, the general idea in the backstepping control is, you saw that given this system, what I can always do, I can find out what is x2 as a virtual control action. So, what is my x2 equal to x2d such that this particular system is stable, which we already have shown, okay, by using Lyapunov function approach. And then again I find out what is x3 equal to x3d, the virtual control action such that the second subsystem along with the first one is stable, like that. We go ahead. So, choose x2 equal to x2d such that the system x1 dot equal to f1 hat x1 x2d tracks x1d. Similarly, choose x3 equal to x3d such that x2 tracks x2d and so on. finally select the control action U2 such that XM tracks XMD. So, what we are trying to do here is that find X2D such that X2 tracks find X2D here, X2 equal to X2D such that X1 tracks X1D in this one. Similarly, find X3 equal to X3D such that X2 tracks X2D, and so on. Finally, here find U such that XM tracks XMD. So, this is called backstepping. Okay. So, this is why it is backstepping. Okay. So, once I told you what is the methodology of backstepping, now I will tell you why this is normally done. The problem with traditional robust and adaptive control is the computation of regression matrix at each design step is tedious and time consuming. Linear in parameterization assumption which is used in robot manipulator is quite restrictive and may not be true in practical situations. So, now backstepping control using neural network. This is the theme of this particular class today. So, I introduce what is backstepping control. Now, we will go in detailed design using neural network. So, design a fictitious controllers for X2, X3 and XM first step. So, consider the first subsystem. The first system was what in strict feedback form, X1 dot is F1 X1 plus G1 X1 into X2, right. So, define a Lyapunov function for this subsystem. Already we have already seen that for such a subsystem V1 dot is half E1 square, where E1 is X1 minus X1D, because we are trying to design a tracking controller. We can easily would have shown V1 equal to half X1 square if I am simply stabilizing around the equilibrium point. Instead, this is for tracking controller. The objective is to design a tracking controller that my plant should follow desired trajectory. So, its time derivative is given by V1 dot, sorry, this is not V1 dot, this is simply V1. So, V1 is half E1 square and V1 dot is E1 into E1 dot, which is E1, and E1 dot you can easily see this is X1 dot minus X1D dot. And what I can do, this X1 dot I can bring it from here, which is F1 plus G1 into X2 minus this quantity which is X1D dot, right. So, they are choosing the fictitious controller for X2, because you see that here we found out V1 is to be this. Now, I want to make V1 dot negative definite. So, X2 is my virtual control action. So, what should be my X2? So, that V1 dot is negative definite. So, that is possible if I select X2 is G1 inverse minus F1 plus X1D dot minus K1E dot. If I select this and put this X2 in this quantity, so I get V1 dot is minus K1E1 square, which is negative definite, but X2 is a state, not a control, as we have already saw it. So, its desired value is given by X2D. So, this is not a control action. So, what I can say that if my X2 is following this desired value given by G1 inverse minus F1 plus X1 desired dot minus K1E1, then my first subsystem is stable. But you see that I normally do not know why we are utilizing neural network, because this F1 you see we have assumed this f1 to be unknown. So, because this f1 is unknown, I replace this f1 by f1 hat, which is x2d desired. So, corresponding the error variable E2 is x2 minus x2d. So, then we can now write x1 dot is f1 gx1 g1 x1, this is my original equation, and I add to this minus g1 x2d and subtract also the same quantity, and I replace this x2d by this quantity, this one. By doing that, I get x1 dot is f1 plus g1 e2 minus f1 hat plus x1 desired dot minus k1 e1. K1 simply a positive constant here. So, if you do that, you see that I can take x1 d dot to this other side, and I can write this to be E1 dot, okay, because my E1 is x1 minus x1 d. So, this is called closed loop error dynamics. Which is f1 minus f1 hat minus k1 e1 plus g1 e2. So, differentiating E2 gives E2 dot is x2 dot minus x2d dot is f2 plus g2 x3 minus x2d desired dot. And following the same analysis before, we choose a fictitious control for x3, this one, in such a way where x3d is g2 inverse minus f2 hat x2d dot minus k2 e2 minus g1 transpose e1. Then we get the second closed loop error dynamics. E2 dot is f2 minus f2 hat minus k2 e2 minus g1 transpose e1 plus g2 e3. You see that this g1 transpose e1 is to compensate the effect of coupling due to g1 e2. You can actually derive this from the first principle, the way we found out e1 taking the Lyapunov function. Similarly, also you can find out what is e2 dot. Okay. This process of finding the closed loop error dynamics for each subsystem, each scalar differential equation is continued. The design is continued till the EM1 equal to xm1 xm minus 1 minus xm minus 1 desired is stabilized. So, this is what. So, we found out the error dynamics. After we did that, then the last equation EM is given by xm minus xmd. This, the red derivative is time derivative of that is fm plus gmu minus xmd dot, because xm dot is given by this quantity already by strict feedback form, and choosing u, again this is found out using again Lyapunov function approach, when we assume that fm is actually fm is known, then this is actually the control action that will stabilize. So, then this is my final closed loop error dynamics. EM dot is fm minus fm hat minus km em and minus gm minus 1 transpose em minus 1, where ki I equal to 1 to m are design parameters, fi's are approximated by neural network, and we assume that each f or fi is approximated by w transpose phi, such that phi hat, the estimated one, w hat transpose phi, and phi are the basis function, and you know the phi is the basis function of input. For example, if I go back to my original form, if I want to estimate this f1, then my input is x1, and f2 my inputs are x1 x2, and f3 I estimate, then x1 x2 x3 are the input. So, like that. So, the in case the nonlinear function f i's are known accurately, the above control law is given by this, would give exact tracking of state variables. Okay. However, in most cases these nonlinear functions are not known accurately, hence we approximate these functions using neural networks. In order to keep the approximation error bounded, we use Lyapunov function to find a weight update law w hat dot, because if you get previously this each neural network is represented by w hat transpose phi. Phi is on known basis functions, whereas w hat transpose this weight vector is not known. So, we have to find out weight update law. So, now this is your backstepping controller. We designed what is u, and u utilizes the neural network NNM, whose output is fm hat, and also it utilizes xmd, the information that is given by backstepping approach, because given x1d, I find out what is x2d. Okay. Given x1d, I find out what is x2d, what must be x2d, and this is my the first f1 is approximated by neural network 1 whose input is only x1, second neural network NN2 takes the input x1 x2 as I showed you earlier. So, the output is f2 hat and I get x3d, you can easily see that. We said that here given x1d, I find out what is x2d. Okay. My x2d is in terms of x1d is the input and neural network output f1 hat. Similarly, you can easily see here also x3d is a function of neural network output f2 hat and x2d, and that is what we are seeing here. So, x2d is a function of x1d and f1 hat, x3d is a function of x2d as well as f2d hat, f2 hat, and so on, and u is finally a function of fm hat, which is output of NN neural network mth neural network whose input is x1 to xm, and this is, and also u is a function of xmd dot. Then if I give this to the plant, I have to find out what should be the weight update law for these neural networks, such that the closed loop error dynamics is stable. So, I just represent now the error dynamics that we have already shown. U1 dot is, this is my f1 hat minus k1 e1 plus g1 e2, e2 dot red derivative of error, second error differential is again f2 hat minus k2 e2 minus g1 transpose u1 plus g2 e3 and so on. This is my error dynamics. So, if I define xi to be this quantity, this vector of all the parametric error, tracking errors, and z tilde is my this quantities, you see this quantities are actually f minus f hat, you can easily see that em dot is fm minus fm hat and so on. This is actually, the first one is f1 minus f1 hat, similarly this is fm minus fm hat. So, so this is the my weight vectors, the difference between the desired one that is existent optimal one and the actual one, and k is the parameters, the controller parameters that has to be found out, and phi is this quantity, the known quantities of basis functions of the input x1, x2, x3 and so forth. So, then this each scalar differential equation, the scalar error dynamics and like that m scalar differential equation can be put into one vector differential equation. Xi dot is minus k zeta. Okay. So, this is, you can easily see where this is k zeta, this quantity, and Z transpose phi, this quantity, and H xi is this quantity, because my xi is simply this quantity, and H is the matrix, and H matrix is given by 0 G 1 0 0 0 minus G 1 transpose 0 G 2 and so on. So, this is my H, and it is skew symmetric. The property of this is skew symmetric, and now the weight update algorithm is selected skew symmetric because if I write x transpose H x then that is 0, you can prove that. So, let us take a Lyapunov function for this to be this, and if I find out differential of V dot, so you see you finally get this quantity, and which is if you further elaborate. So, you see that this is due to skew symmetric, this quantity becomes 0, and if I assume Z hat dot is this quantity, and you know the Z is actually the weight vectors. So, if I weight update law is taken by this, then this quantity and this quantity, they are same. So, V dot is simply xi transpose k xi, and k is all positive quantity, and hence this is stable. Okay. So, and it can be shown that B double dot is bounded, hence Barwell's lemma xi tends to 0 means error, tracking error goes to 0. So, what I showed you or we just learnt that this is my weight update law, for which this controller, this particular dynamical system is stable, okay, or this error dynamics, closed loop error dynamics are stable, where neural network has been used to estimate the unknown functions f 1 to f m. Now, we take a example of a robot manipulator, rigid link electrically driven robot manipulator, for which this is our normal expression m q q double dot v m q dot, this Coriolis, this is gravity, this is friction, this is a mistake here, equal to k t I is the current of the motor, electrically driven motor. You know that this is actually torque, and torque is a torque constant into current, and then we can write for the motor, the equation is L I dot plus R I plus K B Q dot is U E, which is the applied voltage, right. And by defining these parameters, A as this, B is this is a taking two link manipulator, this is two link robot manipulator, and defining parameter A, B, C, D and E as this. So, M becomes 2 by 2 matrix like this. The arm parameters L 1 is 1 meter, L 2 is 1 meter, M 1 is 0.8 kg, M 2 is 2.3 kg, G naught is 9.8 meter per second square. So, then you see that my Coriolis matrix is Coriolis force vector is given by this particular expression, and GQ, the gravity force, is given by this particular term. The motor parameters are given, L is again here, R is given by this, KB is given by this particular matrix, and torque constant is given by, because you have two links, so two motors. So, that is why you are seeing these are all matrices. So, desired trajectories for two links are q 1 d is sin t and q 2 d is cos t. So, robot dynamics in terms of filtered error, you see that in the beginning we always represent the robot dynamics in terms of filtered error, m r dot is f 1 minus b m r minus k t I, where f 1 is given by this particular quantity, So, you see that this is kind of expression we can always say that this is stable provided if I can select I equal to desired ID such that R tends to 0. Okay. So, the above aerodynamics may be written in terms of now m r dot is F 1 minus V m r, and now I just represented this. Earlier it was simply minus k T I. Instead of I write I d plus k T eta, and eta is I d minus I. So, you can easily see this is same as my original one F 1 minus V m r minus k T I. This is my original dynamics, and that I am representing in this particular form. So, if I select I d to be of this particular form, okay, and since I do not know what is k T, so I do not write 1 upon k T, I write 1 upon k 1, where k 1 is a positive constant. Then m r dot can be represented in this particular form. So, you see that if F 1 and F 1 hat, they are almost known already, because if it is, let us think about the case when it is known, then I can say this is almost 0, and V m r, this is these V m r and this particular some constant into r, they contribute to the stability. So, all that I have to now show that if I can cancel this, again I represent this particular term, I minus V m r, I bring it here, and this minus F 1, this particular quantity is, this quantity is represented by this expression, and this I express by a neural network. This F 1 hat is represented by a neural network. Then I can represent this, and this quantity is here, and this quantity is represented here, and this quantity is here. So, I can always find some V nu tau in such a way that this term and this term can be cancelled out, can cancel, then this term can be cancelled out this. So, the objective is that find this particular term, so this term first cancels out. Usually k T is not known. The robustifying term nu t is selected so as to suppress the effect due to term I minus k T upon k 1. So, V tau, if I select this, then V k is the upper bound, this V k is the upper bound of this, as the above error equation, this error equation, this m r dot is this quantity, can be rewritten in this particular form. Okay. So, you say that this I am representing by a neural network. This is actually, if m r dot is this, if neural network exactly approximates the function, this is 0. So, then m r dot is this quantity, this is stable, then I have an extra term k T eta, and if eta is bounded, then system is stable. So, now I select u e in such a way that eta will be bounded. For that, eta already I know the desired current minus I. So, L eta dot is L I d dot minus I dot. So, I can represent this in terms of F 2 minus u e, this is the control action. So, what should be my control action such that eta is bounded? So, that is my second one. So, if I find u e as this is my neural network approximation of F 2, and then if I take my control action to be k v eta, then my error dynamics is L eta dot is this quantity. So, you see that if this is 0, that means my neural network approximation is exact, then this is a stable dynamics. So, eta is bounded. So, if eta is bounded, my previous term, this is also stable. Okay. So, now what I have to do, I got two closed error dynamics, m r dot is this quantity and L eta dot is this quantity. So, two closed loop error dynamics in the same manner that we had earlier, this one, the set of error dynamics, similar error dynamics we found out just now, and this two aerodynamics, going by the same principle of defining the Lyapunov function, we can derive that for this the weight update law is gamma 1 phi 1 r transpose, and W 2 hat dot for this one is gamma 2 phi 2 r transpose. Okay. If I do, then the system is Lyapunov stable. By doing that, so this is my obviously my controller architecture, direct adaptive controller architecture for rigid link electrically driven robot manipulator. Okay. So, implementing my previous control law. So, my what I showed that this is my weight update law and my control law is this one, U2 U is this is my control law. So, doing that I get this, you see, desired and actual, link 1 position tracking, link 2 position tracking here. This is PD control of rigid link electrically driven manipulator. Okay, by taking this is a PD control, and you see that the proposed backstepping control tracking error is vanishes. So, you see that if I do simple PD control, a lot of tracking error in both joint 1 and joint 2, but once I implement the neural network based backstepping control, my tracking error goes to 0, and this is my error, which is this is control input, okay, and this is PD control actions, and this is backstepping control action. So, observations: the problem of weight initialization does not arise since these are all taken 0. Tuning algorithm ensures the weights are bounded. PD controller requires large gains which might excite high frequency on-model dynamics. NN control neural network based controller improves tracking performance. Summary: what we discussed today is NN based adaptive controller, which was revisited in the we discussed in the last class, Lyapunov based design, backstepping using neural network, and we demonstrated the efficacy of backstepping using a rigid link electrical driven motor. Thank you very much.